All right, the title is Fearful Symmetry. This is the slide I thought most about. Can we solve ideal lattice problems efficiently? They have that scary symmetry, you see. Huh? Well, I guess maybe there's a tiger looking. I don't know. Yeah, it's from that. But really, it's just the phrase fearful symmetry. I wasn't trying to make an illusion of any sort. It's just a cool phrase. Okay. That didn't work. Oh, there we go. All right. So I guess sort of the main question of this conference is, can we efficiently break lattices with certain types of symmetry? So for example, if a lattice has an orthonormal basis that's hiding inside of it, can we recover it? Okay. Or for the case of ideal lattices, ideal lattices have structure related to ideals in algebraic number fields. Can we take that structure, that algebra, and somehow combine it with the geometry of lattice reduction techniques and actually break ideal lattices? So I'll be talking about the Gentry-Szydlo algorithm, as it's become known for the purpose of this conference. And then Mike will follow up on the difficult details. You know, I'm just doing the easy part of it. The algorithm combines sort of geometric techniques and algebraic techniques in, I think, sort of an interesting way. And one wonders. Okay. So maybe it will actually be a whiteboard talk at some point. Anyway, so I'll be going over those techniques and hopefully stimulating some thoughts about, you know, how we can better combine algebra and geometry to get, you know, algorithms that really break ideal lattices and destroy all the wonderful crypto systems that we've developed over the past few years. Yeah, so it's a personality difference, I guess. I mean, it's, you know, how you approach the world and other people. You know, I guess we like to we're a little rougher. I don't know. But yeah, so I mean, mathematicians are sort of looking for structure, I guess. You know, which is sort of a passive, but albeit beautiful thing, whereas cryptographers are looking for machines that do things. Yeah, okay. I'm just stereotyping. Okay. So anyway, the Gentry-Szydlo algorithm says this is just, you know, actually I'm a little worried that this talk is maybe too easy for this audience. Well, okay. Okay. But yeah, so you probably, I don't have to explain these terms, but I will eventually. But I just want to say right from the outset sort of what the Gentry-Szydlo algorithm does. What it says is that if you have what I'll call a circulant lattice, okay, this is a lattice, well, I'll describe it later, but I'll go ahead and describe it now, I guess. So basically for every, you know, vector in this lattice, the sort of the rotation of that same vector is in the lattice. So if you just kind of cycle the coefficients one by one, all of these are also in the lattice. So if you have a circulant lattice that happens to have, it's not only a circulant lattice, but it happens to have a circulant basis, which is not true in general of all circulant lattices, then what you can do is, given any basis of L, if the vectors in B are actually orthogonal, then you can actually recover those vectors. You can actually recover that really good basis that's underlying there. Yeah.
Oh, so circulant has to do with some embedding of the lattice into Rn?
Yeah, we're going to deal with basically cyclotomic fields. Yeah, so it's going to be...
Okay, but it's not like an intrinsic property for lattice.
What do you mean by that?
I mean, at least like the way that you present this lattice as being circulant is you like demonstrate as a subset of Rn, and it happens to be...
Yeah, basically, and yeah, so this is sort of coming from entry. We're doing, you know, modulo x to the n minus 1, not even a cyclotomic field actually, and so then we're just looking at the sort of the coefficient embedding of that ring. Yeah, so that has very much to do with how you embed things in.
But you're saying circulant lattice doesn't necessarily have to be circulant basis. Circulant basis means what?
It means that it's a basis you can actually write out, and it's a matrix where the columns just sort of cycle. Yeah. Right.
So do you assume that the entries are integers?
Yeah, why not?
Just getting started.
Yeah, I'll assume they're integers, or at least rationals. Yeah. Yes. Yeah. So I'll just try to go forward at the right time. Okay. So even if you know, B is not necessarily a very good basis, so suppose we're looking for that basis B, and if we're given sort of information about its shape, certain information about its gram matrix, actually, the B times B transpose, then in that case, even if it's not orthogonal, we can still recover that target basis B in polynomial time. Okay. So if you, when it's sort of restated in more of an algebra, you know, normal proper algebra terms, if you have a principal ideal in a cyclotomic field represented by some z basis, then basically given any z basis of that ideal lattice, of that principal ideal, if it happens to be the case that v times its conjugate is 1, or some constant, then we can actually find that element in polynomial time. If you look at it as a, I guess I'm kind of thinking of it as a polynomial in.
Okay, so you mean like it's a rational?
Yeah. Yeah. So those are the. I have to do some translation for the word integer to think of algebraic integers. Normally, I just think of real rational integers. So, and then you have an analogous thing to previously. Even if v is some nasty-looking vector, if you're given v times its complex conjugate, which is basically the relative norm in the index 2 subfield of the cyclotomic field, the relative norm, then we can find v in polynomial. Okay. So hopefully by the end of this talk, you'll have a better understanding of what's going on. So, all right. So let me give you a. I'll try. Yeah. Yeah, by ideal lattice, I just mean the geometric lattice just associated to that ideal as a z basis. Okay. So what I'm going to talk about is I'll sort of talk about an early version of entry sign, and this came up in cryptanalysis. I'll talk about some sort of failed attempts at cryptanalyzing it, and then I'll talk about our actual attack. And then towards the end, if I have time or we have the inclination, then I'll try. I'll talk about some extensions of the algorithm. Okay, so so we were trying to break an early version of the Gentry-Szydlo signature scheme. Gentry-Szydlo uses polynomial rings like this, and so I'm not going to go into the whole signing and verification process because they were a little complicated. Oh, yeah, sorry, that's unpleasant notation for mathematicians. It means that I'm additionally reducing things modulo q in that ring R. It doesn't have to be. Yeah, an integer, yeah. Okay, so the signatures have the form v times yi. Okay, you can get lots of signatures, right? You should be able to ask for lots of signatures and not produce more signatures, right? So you can ask for lots of them. And then v is the secret key. And then and these yi's are correlated with the message in some way, but they're kind of statistically sort of random, geometrically just sort of random. And the v's and the y's are sort of small, meaning that they have coefficients kind of much less than q. But it turns out that, they're just big enough so that they're actually, when you multiply them, there is some wrapping modulo q. So some of the coefficients will be bigger than q. Okay? So we wanted to break that, not analyze its structure and actually break it. So the first part of the attack is we actually found a way to lift the signatures in the sense that we found a way to take things that were originally reduced modulo q and sort of unreduce them so that they were exact multiples in the ring R. Okay? I won't explain that because it's not, it was kind of a fun little attack, but I'll sort of skip that one. Yeah, it's very heuristic, so it's, yeah, there's nothing interesting theoretically there necessarily. So. It's something that we actually coded and we had running times, so it's not, we didn't have any theorems. Yeah. All right. So, okay. So suppose now that we have these unreduced multiples of the secret key, what do we do at this point? Any answers? Well, I wouldn't say it's trivial, but it's solvable.
Tell me, what is the hard part to remove the mod q or once the mod q
Well, I kind of wanted to hide, leave some suspense for the solution, but there were kind of three parts to the attack. One was unreducing things modulo q. The second thing was sort of an sort of an averaging attack, which was also heuristic in a sense, but more easily analyzable to obtain a certain quantity. And then the third part of the attack was using that quantity in combination with the signatures, which basically give a representation of the ideal V.
Okay, so all parts play quite well, but yeah,
None of them is, yeah. So the second and third parts are more interesting for our purposes. So if you think they're trivial, then we can skip them. No. Yeah. This is the meat of. I'm just asking. I want you to think a little bit about, what is the best approach from here, right? So, one thing we can do is we could try to set up a lattice in which V is the shortest vector. Okay. Again, I think maybe I made these slides too easy, so you could probably see that right away. And yeah, an algebraic approach, I mean, you might try to take the GCD of these things in some sense. I mean, it kind of looks like a GCD, right? I mean, except, as you might guess, it doesn't really work. Or should we try something else? So what do you think? What's... Well, I'll tell you eventually, but if you give me a new idea, I'll tell you why it doesn't. You're not allowed.
But the GCD is by definition just ideal, right? You know it already.
Exactly. Yeah. So it doesn't really have any. Okay. So so I'll give first some sort of naive attacks on this. So I had all these beautiful pictures of lattices, so I thought I should use them, even though you probably all know what lattices are. So lattices look like that. The grid of points. You know, so they have good bases and bad bases. You know, basis is a linearly independent set of vectors that generates the entire lattice via hops. Okay, well, I kind of overdid it with the pictures here, but but a good basis kind of tessellates the entire space in terms of sort of orthogonal parallelepipeds. Not sort of orthogonal looking ones though. Okay, so here's a bad basis. Just in that, because the vectors are sort of less orthogonal. They still define a parallelepiped. It has the same area, but it's more skewed. Tessellate space. So you can define various hard problems on lattices. I should probably move this way so you can see. So these are hard problems that we care about in crypto. So the shortest vector problem, given a basis. Can you find the shortest non-zero vector in this lattice? Looks pretty easy in 2 dimensions, and it is. I mean, there's a sort of Euclidean type algorithm where you can, if you start off something skewed, you can kind of subtract things off one another until you get to this point. In 100 or 200 dimensions, it's a little more difficult. So you can have the shortest independent vector problem. Output sort of an entire independent set of vectors that's short. My clicker's a little slow here. Closest vector problem. Basically, you try to find, given some vector in space, you try to find the vector that's closest to it. And there's the bounded distance decoding problem. This is basically the closest vector problem under the promise that the target vector is really close to the lattice, in the sense that, it's like maybe 100 times closer to a certain point than it is any other point. In crypto, we mostly care about approximate versions of these problems because that's what we base security on. We can't, base the security of crypto systems on exact shortest vector problem. We don't know how to do that. In fact, we kind of believe it's impossible since that's an NP-hard problem. We don't know how to base, public key crypto systems on NP-hard problems yet. We don't know that it's impossible. We just don't know how to do it. So we end up basing crypto systems on approximate versions where their approximation factor is, for example, some polynomial in dimension n. And what I mean by bad basis, you can kind of formalize it. Sort of the canonical bad basis is the Hermite normal form. It's a basis of the lattice such that given any basis of the lattice, you can compute it efficiently. It's upper triangular. It has, diagonal entries are positive. It has a certain, other nice properties that make it canonical. In terms of actually using it, it's nice because it has a compact representation. So even though it's a really, really bad basis, the number of bits needed to express it is pretty small. You can bound that pretty easily, so it's easy to work with in that sense. As I said, it's efficiently computable from other bases. And it's, in some sense, the baddest basis because it's canonical. You can compute it from anything else, so it reveals really nothing more than any other basis does, right? You know, so if you're a cryptographer, you want to make the public key of your crypto system the HNF of the lattice, because it, you know, some other basis might leak some information. This one doesn't leak any more than anything else. Okay. So in terms of lattice reduction algorithms, what do we have? These are just general algorithms. Well, we have LLL, of course, which outputs a vector in polynomial time, but it could be as large as, say, 2 to the n over 2 times the shortest vector in the lattice. So that's a big approximation factor away from the shortest vector. On the other hand, in the other extreme, you have algorithms that output the shortest vector, but in exponential time. Huh? 4 to the n, okay. Well, that's what I meant by roughly. It's, it's 2 to the n, 4 to the n, what's the difference? Okay. It's very literal answer. Okay. In between, we have algorithms that say output a 2 to the square root of n approximation of the shortest vector in 2 to the square root of n time, basically, up to some factors that I'm ignoring. Okay, so clearly we don't have, if you want to set n big enough, we don't have algorithms that are both very fast and very effective. Yeah.
The basis always has, that you're talking about here, has coefficients in integers, right?
Yes.
Okay. So it has an embedding with integer coefficients.
Yes.
Okay.
So is it important these aren't actually lattices, but they're actually embedded lattices with symmetric structure?
I mean, you can also use the canonical embedding, and basically any of this stuff here would work also.
The algorithms can also work within the ground matrix of the lattice. You can work without the embedding.
For those two algorithms.
Yeah.
Yeah.
But yeah.
Okay, so let's go back to our cryptanalysis problem. So what can we do? Well, we can try to make V be a short vector in some lattice and apply LLL, for example, or some other lattice reduction algorithm. Well, it seems kind of hopeless because, I mean, yeah, you can construct vectors where V is the shortest vector. So in principle, you can obtain it using lattice reduction, but in really large dimensional lattices. So if n is large, then it's kind of hopeless. But I'll go over the approach anyway, just so you know. So just let L, the lattice you look at is just the set of all the lattice generated by these multiples of V of x. I mean, with high probability, these y's are relatively prime. So V of x is going to be in there, right? So that's your lattice. But as I said, it's, well, as I'll show you, I guess, particularly what the lattice is, it has a high dimension, and it does have a lot of structure, but generic lattice reduction algorithms don't exploit it. So in particular, this is related to ideals, I guess, as we've sort of already said. So you probably know the definition of an ideal in some ring R. Well, it's a subset of R, and it's additively closed. So the additive closure property sort of basically means it's a lattice. And it's closed under multiplications with elements of the O. Yeah. Yeah, I mean, I guess you have to have some non-triviality conditions. But yeah, so for example, an ideal, simple ideal is 3, the multiples of 3. all the polynomials that are divisible by 3, if you're looking at it in the coefficient embedding, which I prefer to do, sorry. And then in the polynomial ring, all the multiples of some polynomial v of x. Right? Okay, these are principal ideals because they're generated by one generator. But it's not true in general. I mean, in general, in polynomial rings, not all ideals are principal. In fact, most of them aren't. But here, we'll be dealing mostly with principal ideals, just because of the nature of the cryptanalytic problem.
And great. So going back to the previous slide, you don't need to go back, but you're basically assuming that the yi's, they generate R.
Yeah.
Yeah. So that's
Yeah, I mean, they're generated sort of independently in a certain sense, and so with high probability after.
yeah, but that was basically the assumption.
Yeah.
So that's not going to be the,
Yeah.
you take the ones together.
Yeah.
And
Yeah.
practically, you could just get a lot of multiples of C. And so you just keep trying more and more and more, and then you get a whole bunch of C. What guarantees that the generator is the shortest geometry?
Well, that's just how it's generated. It's, I mean, in the actual scheme, it's generated as a short polynomial with sort of random and independent in some sense. I don't remember exactly. Coefficients from the set, you know, -1, 0, and 1. And so if you generate something like that, it's very likely to be the smallest. Or it really in the scheme, it suffices to obtain any vector that's short enough. In this ideal. So if it happens to not actually be the shortest, it doesn't really matter because you can use whatever really short vector you obtain as the secret key, I think. I'm not sure about that for the, but I think so. And as I said, when I say ideal lattice, I just mean a representation. I'm thinking of the ideal represented as a z basis. Okay. Okay. Can you see that? Okay. So, so if you look at the lattice of multiples of some particular polynomial v of x, it happens to have a basis that looks very nice. This is a circulant basis. Okay, so it's just, you know, the coefficients just kind of rotate like this. And so, I mean, you can sort of see that because, well, this column corresponds to v of x. And this one, if you just multiply it out, v of x times x is just, well, it's blue. No. It's this, that column there. And so they're just all generated cyclically like that. And so that's, and so when you take like, you know, if you take some linear combination of these columns, what's happening is that, you know, some linear combination W of these columns, what happens is that you're actually just sort of multiplying the polynomial W of x times V of x, essentially, because you're taking the sort of the 0th coefficient of W and the first coefficient, and it has the effect of essentially outputting V of x times W of x. Oh, there's some stuff on the bottom there. Okay. So this is, I'll call this the rotation basis of V of x. So yeah, this is all, maybe by now you believe that these slides are actually too simple so far. But anyway, so you can see pretty clearly that the basis, the rotation basis had, well, except for certain perverse cases, you know, involving zero divisors, but, you know, typically for sort of a random looking V of x, the rotation basis that I put on there has rank n. And so that, you know, that means the lattice problem that you're trying to solve, this is exactly the same lattice that we constructed from the signatures, the v times yi's, which are the multiples of v of x. This lattice has dimension n. And if n is big enough, then you're just not going to succeed in finding v of x. Okay, so as you can see, there's a lot of underlying structure there, but generic lattice reduction algorithms don't exploit it. Okay, So why can't we just take the GCD? Well, Hendrik, already spoiled.
Sorry about that.
So why can't we just take the GCD like we could do over Z? I mean, if we just had a lot of V times yi's over Z, wouldn't be so hard to recover. Well, it would be a one-dimensional lattice, so it wouldn't be very interesting. But we could recover V pretty easily, up to units, because it's defined only up to units. The problem is that in this polynomial ring there are lots of units, not just the trivial torsion units, which are, x or the nth root of unity, if you like. But you just take that to the nth power, it's a unit. But you also have sort of non-torsion units that look like this. No?
If you substitute x equals 1, you get k, which is not a unit in Z.
Oh, I was thinking x is like a primitive nth root of unity.
Right,
Yeah.
but in this ring R, it won't be a unit. It will be a unit if you factor out not by x to the n minus 1, but by the x to the n minus 1 over x minus 1. So you have to remove one of the components.
Okay, so you're happy with...
It's almost a unit.
Make sure it does the right thing with the other.
No.
Okay.
Good talk about it.
Okay. All right. So basically, what we have, we have an infinite collection of units, basically given certain sort of basis set of non-torsion units. You can generate, sort of arbitrarily large products of these things, and you have infinitely many different units in this ring. So V is not even uniquely defined unless we pay attention to the smallness condition. And so this GCD attack, well, as Hendrik said originally, I mean, you're really only taking the GCD of ideals. So you already have the ideal. And so that's the only meaningful sense in which you can take the GCD. All right, so let's talk about our actual attack. So as I said, the first step was to lift the signatures to get these unreduced multiples. The second part of the attack is we're going to do an averaging to obtain a certain quantity that's related to the secret key, which is basically V times its conjugate, which is, as I said, the relative norm, related to the relative norm of the element in the index 2 subfield. Okay, so you're just, I mean, a regular norm would be you take the, the product of all the different conjugates of V, and you get something in Q. Here you're just going down to the, taking the relative norm with respect to the index 2 subfield. And then once we, step 3 is that once we have this quantity, this relative norm of V, what we can do is take that and a basis of the original ideal lattice, which we presumably have from the signatures, and we can recover V from that. Okay, so what is this thing, this relative norm? Well, I mean, this is not very nice algebraically, but I tend to think of it as you just have this polynomial, modulo x to the n minus 1, and you just replace the x with x inverse. And what you get is, what happens is that basically the order of the coefficients reverses. So I'll call it the reversal of V instead of the conjugate. Yeah. Right. So it also has a geometric meaning, this thing, the conjugate. So if you look at the rotation basis of this, what happens is that it's actually the transpose of the original one of V of x. Okay. So originally we had V0, V1, V2. Now it's just the transpose. And you can see how that has a geometric meaning. So this is a very useful quantity geometrically. So basically, when we obtain this quantity, we have the gram matrix for B. Okay, and that is basically all the set of mutual dot products of vectors in B, which is obviously a lot of geometric information about the shape of the basis B. So okay, if we obtain this quantity about V, we obtain a lot of geometric information about V's shape, essentially. This is just the conjugate.
No, B and B. So B
V and B.
is the basis for the lattice.
B is the rotational basis of V. It's just the matrix of V and its rotations. And what happens is that if you just multiply B times B transpose, you get the rotation basis of this value here. Okay.
So what did you do before to estimate the value?
I haven't gotten to that yet.
Okay, you said you.
Yeah. Right. So as I said, it contains all the mutual dot products. There's a lot of information about the shape. It doesn't really give you sort of the orientation of V in space, but it does give you kind of the shape of that basis in some sense. And I've sort of already gone over this. I mean, you can phrase things algebraically instead of looking at the particular coefficient embedding that Gentry uses. So, I mean, we've really been working in mainly, I mean, you know, Gentry uses the ring modulo x to the n minus 1, which is not quite a cyclotomic ring, but when n is prime, it's very close. And so most of the interesting stuff is happening in the cyclotomic ring. The additional x to the x minus 1 doesn't really provide any more security. So you can pretty much just look at what's going on in the cyclotomic ring. Okay? And so, you know, what we've been talking about in terms of polynomials, you know, looking at polynomials modulo x to the n minus 1, we can you know, instead use cyclotomic polynomials and say, well, this is just isomorphic to the nth cyclotomic field. Yeah, and you know, so there are various different embeddings. And I mean, the most interesting one for our purposes is that when you take the product of these two embeddings here, that corresponds to the relative norm in the index 2 real subfield. Right. Yeah, so all the embeddings correspond to, you take some nth root of unity, and you send it to some other primitive nth root of unity. Yeah. So sigma 1 is just the identity, and sigma minus 1 is you send it to the inverse.
So that's the same as complex commutation then?
Yeah, yeah. Yeah, so exactly this quantity V times V bar is just V times its complex conjugate. You're represented as, you know, it's a polynomial. Or in some embedding. Okay, so now let's actually recover this, this quantity. This is AR, it's just average. So what we're going to do is we're going to take all these signatures and multiply them with their conjugates, right? And then, well, what happens is that you can, it's hopefully not too hard to see that you can just move out the V times V bar, and you get that times a product of these relative norms of the yi's, where the yi's are just sort of kind of random and independent, and so they behave sort of, well, you can sort of analyze what they converge to. Okay, so in particular, if you just look at a particular yi times yi bar, so look at the 0th coefficient of it. Well, what is the 0th coefficient of y times y bar? Well, maybe it's maybe easier if you go back to thinking of it in terms of the gram matrix, right? So if you're multiplying the gram matrices of these two things, what happens is that the 0th coefficient is just the length squared of the coefficient vector of y. And the ones that are off the diagonal are, well, they're dot products of different vectors. So they're kind of shorter, they might be negative, and they're kind of sort of randomly distributed in some sense. But the ones on the diagonal with this gram matrix are big, right? So what you get in this average is that the 0th coefficient of this thing is sort of a big constant. And the other ones sort of converge sort of slowly, with the inverse of square root of r to 0. So when you take y times y bar, you represent them as polynomials. You multiply them together. The constant term. Sorry. Yeah, constant term.
So if the coefficients of yi are reasonably big, it could take you a long time until this is actually enough to determine the bar. And r could actually be very big.
Well, the ratio between, even if you're saying the coefficients of y are big, the ratio of the biggest coefficient, the constant coefficient, versus the other ones will still be pretty big. So that.
But in order to actually figure out what VV bar is, don't you need the other coefficients of YR to actually be like less than 1, if not smaller?
No, because it's all up to scaling. Yeah. Yeah, exactly.
Fine, but they need to be less than like the size of the coefficient of VV bar.
Right. You need the ratio to be big enough so that you can just sort of round and obtain the coefficients of V.
So I guess the problem becomes if V is large relative to the y.
Yeah, or if V is just large, period, it's a problem to obtain the exact coefficients. Right. Okay. So yeah, as I said, it's the YR thing converges to some known constant, somewhat slowly, but not too slowly, and so this average converges to V times V bar. As I said, the imprecision is inverse square root of Q, square root of R. So in the particular case of entry signatures, the coefficients of V actually are small, though. So this is good enough for us. So we just, have to take a polynomial number of samples because, well, the coefficients of V times V bar are polynomial. And then eventually you can just obtain it by rounding.
So does it help you that you know which ideal VV bar generates? So that you can round it to an element in that ideal?
Yeah, you could create a lattice problem even with fewer signatures, find out where it is.
Yeah.
Or not, or you could just keep going more and more and more.
Have you run into problems with, I'm sure like YR has a big constant term, but like its constant term might not actually be an integer.
It still doesn't really matter. It really all has to do with the ratio of the constant term with the other terms and how much pollution those other terms introduce into the.
But you will sort of find VV bar up to scaling. You have to figure out which scaling actually gives you.
You have to know what constant this YR term is converging to, and then you just sort of try to divide.
Okay.
Yeah. So you know that the distribution of the YIs. Okay, they're not. That's known. Okay, so that was the averaging attack, and now I'll describe sort of the meat of the algorithm. So okay, at this point, we've done the averaging attack. We have this quantity V times V bar. We also have the ideal lattice, V, and we want to recover V.
Just to be clear, it's not just the ideal lattice, it's actually the ideal.
Yes, the ideal. But yeah, being imprecise, but I just means some representation of the ideal. Some as a...
As an ideal, not as a spiritually gram matrix for a lattice.
Right. Okay, so I'm going to give you sort of an inaccurate description first, but hopefully you can bootstrap that into something that's more accurate.
So follow up on that, it was just a Z basis for it as a lattice is enough for your
Yeah. All right. So okay. So this is not going to be completely accurate, and you're going to see all sorts of problems with this, but hopefully it'll help. The simplification will help you think about it, simplify things a little bit. So first, we pick sort of a big prime, which is congruent to 1 mod n. Okay, and it's it's bigger than the lattice reduction approximation factor. Okay. Next, we're just going to take the basis that we have for I, and we're going to compute a basis for I to the p minus 1. You can probably see a problem already. It'd be kind of hard to represent that since p is exponential, but never mind that. Now we have this basis of the power of I. We're going to reduce it using LLL to get some particular element, v to the p minus 1 times some w. V to the p minus 1 generates I to the p minus 1, so it's times some w, where w is less than the lattice reduction approximation factor. Okay, so by Fermat's-Little theorem. So we'll have, the v to the p minus 1 is congruent to 1 mod p, and that also works out because p is 1 mod n, and so everything sort of lines up. And so if we have that, and we obtain this v to the p minus 1 times w, then what can we do? We know this is 1 mod p, so we get w mod p, right? But w is small. W is smaller than p. So we get w exactly. Yeah. All right.
I have a question.
Mm-hmm.
Say reduce it using LL to get v to the p minus 1. Do you mean where v to the p minus 1 times w is short?
No, I mean reduce it to get, well, you're seeing the other problem. So just applying LLL here to this ideal makes a promise about the size of the elements in the reduced basis, right? It doesn't make a promise that the small elements in the reduced basis have the form v to the p minus 1 times something small, right? It could be that v is very skewed, and so when you take v to the p minus 1, it sort of becomes even more skewed. And what w is doing is just sort of offsetting that skewedness to get it back to something sort of orthogonal. And so in that case, w would be very large because it has a lot of skewedness to sort of offset. Okay?
So you start from a lattice where v is the shortest vector, correct?
Yeah. So when you take I to the p minus 1.
V to the p minus 1 is still a generator, a principal
Yes.
generator, but it's not the short.
Yeah, definitely.
So
Yeah.
if I give you an upper bound, it tells you that there exists a vector of this length in the lattice.
Well, just by the determinant, the norm, you can say that it has certain short vectors. And if v starts off, its canonical embedding has, what it evaluates to with a different, nth roots of unity. If that starts off a little unbalanced, that exponentiation is just going to amplify that imbalance.
Yeah.
And so most likely, if V starts off a little skewed, V p minus 1 is going to be extremely skewed, and it's definitely not going to be the shortest vector in the lattice anymore.
Yeah. You still know that LLL gives a vector of this form because it is a lattice vector
Yeah.
and everything in the ideal is that form. Now, LLL
It's just that W is not necessarily going to be small.
Would you know is
LL makes a promise about the length of this, but not.
So how do you get this bound on W?
I haven't told you that yet. That's a problem that you're supposed to notice with this approach. Yeah.
Oh, is it a problem? Or
Yeah.
it is?
So far, it's a big problem.
What you will talk about? Well, he's going to talk about that one.
Oh, because I just want to, eventually we are going to use LLL, and so I want to make this, yeah, I mean, that was, the 2 to the n over 2 was meant to be suggestive. All right.
So, yeah, are you making a false statement? Or,
Yeah, it's a warm-up.
okay.
It's a warm-up. It's an approach with big holes in it.
Yeah. So it's not that you can show that it's non-trivial, you will show it. It is not true.
It is not, yeah, it's not true so far.
That in general, W is not.
It's something with that we can build on. It has big holes in it.
V to the p minus 1 is 1 mod p,
Mm-hmm.
and p is sufficiently large.
Yes.
Wouldn't you get LLL, you can think of LLL as working modulo p if p is sufficiently large. If p is larger than what
Well, I was hoping to, I'm not work, when when I'm doing this lattice reduction here, I mean, I actually do want to take I don't want to reduce modulo p when I'm doing a lattice reduction. I want to obtain this.
So PZN is not a sublattice of the input to a, so the lattice you give to a LLL?
No,
Yeah.
it's unreduced. And then the last step is, well, from this, gigantic quantity here. Well, okay, sorry. So once we've recovered W is small. We recovered mod P and hence exactly. Once we recover W exactly, we have V to the P minus 1 exactly. Right? And then from this power of V, we can get V. So that's the plan. Okay, so first big issue, how do we guarantee that W is small, right? So like as we were talking about, LLL guarantees abound on the vectors that it actually outputs, which is this V to the P minus 1 times W. But, what it doesn't say anything about V and W independently. In particular, it doesn't say that W is small. And like I said, maybe it wasn't quite understandable, but if you just imagine what happens when you have an initial V and you just evaluate it at the roots of unity, and then you take that by some big power, what's going to happen is that at some roots of unity it's just going to be gigantic, at others it's going to be microscopic. It's going to be this very unbalanced thing. And what LLL is going to do is it's going to try to find a W that offsets all that skewedness and exactly counterbalances that to make it sort of more orthogonal. So W is really going to be very skewed itself.
So you're just saying, you run LLL on that lattice, and you get a reasonably short vector, which is of that form, but W could be big.
Yeah. Yeah, W could be very big. It's not the end of the story. Okay, let's see. I'm not going to leave it there. All right. All right. So so how are we going to solve this problem? So what we're going to do is we're going to try to what we really want to apply LLL to are the multiplicands of V to the P minus 1. If we could, we'd like to act just directly on those. and just sort of remove the effect of v to the p minus 1, right? Because that's what we want at the end. We want the multiplicand to be small. So if we can just get LLL to act on the multiplicands as it normally does on vectors that it's actually, given, it should output, some w, v to the p minus 1 w, where w is actually small. If we can, if we can figure out some way to just act on these multiplicands. So, and that's what this value v times v bar is going to allow us to do. V times v bar has essentially all the information that we need about the geometry of v, the grand matrix, the mutual dot products, to exactly cancel things out. So we can sort of, so even though we're given some, the actual basis is for v to the p minus 1, we can use this quantity, we can sort of take it to the p minus 1 power in some sense, and use it to sort of straighten things out in the basis so that LLL is only acting on the multiplicands. And we'll get LLL's guarantee there.
So basically, you get LLL on an ellipsoid at the norm defined by this value?
We literally sort of use these to divide things out. So I'll go into a little more detail about that later. So this is a sketch. Okay, go ahead. No.
So why is LL guarantee this form?
Well, it does generate the ideal v to the p minus 1. So it has to be v to the p minus 1 times sum w. LL, as I said, LL doesn't guarantee that w is short.
So if we turn some vector and we know that there's a v and a w, so that satisfies this.
Yeah. Okay. All right, so that was just a sketch of our approach to this first problem of how do we guarantee that w is small instead of the overall quantity. Second issue is, to get our approach to work, it seemed like we needed p to be exponential in n, okay, to use the LLL bound. The obvious problem with that is that if we actually try to work with I to the p minus 1 or v to the p minus 1, it's not clear how we do that. Because if you actually want to write it down, it takes an exponential number of bits. Maybe there's some way, but certainly not clear. So this part, I said, was the complicated part, so I left that to Mike. I will go over sketch just so that there's some redundancy in our presentations, which will probably, hopefully, help you.
How far are you through your lecture? 80%?
I'm
20%?
I'm like 75% through. Well, 70. What do you think?
People are interrupting now.
Take a break. Do we take a break? How many people want to break now?
Okay.
Okay, 5 minutes, 10 minutes? 7-minute break.
Okay, so I'll just review very briefly, just so we don't start in the middle. So we're reviewing sort of the complex part of the GS algorithm. I gave you this strategy with all sorts of holes in it that we're trying to repair. And I gave you a sketch of how we repair the first one. Basically we just want to act on the multiplicand. So what we do is we have this v times v bar quantity sitting around, which represents essentially the geometry of v, the shape of v in some sense. And we're going to, I'm not giving you details yet, but we're going to use it to sort of cancel out v's geometry so that we can actually, LLL can actually act directly on the multiplicands. And now I'm going to talk about the second issue, which is that, well, we wanted p to be exponential in n, and we can't actually do that because that's not efficient to work with ideals and elements that are that big. So, and I said Mike will go over this, but I'll give you a taste. And so you should badger him with the hard questions. Okay. So we do, in fact, use a P of the form that I described. It's really big prime, bigger than 2 to the n over 2. So we are actually going to do that. And we are going to think about the quantity v to the p minus 1. But we're never actually going to write it out. We're somehow going to treat it implicitly. So what's going to happen? Mike's going to give you the details on this part. But what we're going to do is we're going to use LLL to create a chain of polynomials, right? You might think of, well, it's kind of difficult to describe what the chain of polynomials are without actually getting into them. But they're kind of like of the form, I think it's, well, I have to go back and make sure I'm not making an error, but there's something related to like v1 times v0 squared, v2 times v1 squared, v3 times v2 squared, and so on. So that, I might have gotten the reversed, I don't quite remember. But such that this chain of polynomials will allow you to, in some sense, do some sort of repeated squaring, some high degree exponentiation on v0 implicitly. It'll all be sort of unpacked into this chain of polynomials, but okay. So I'll leave it at that and let Mike describe the details. Now let's just imagine that we have these polynomials that represent implicitly v to the p minus 1 and w. Okay, and these polynomials are not mod anything. They're not mod p or anything like that. Okay. Now the rest I can sort of explain pretty well, I think. So from the chain, we'll actually be able to compute this quantity w modulo p. Okay. All these polynomials in the chain will be small. We'll be able to reduce all of these polynomials modulo p, operate on them there, and that will allow us to get this quantity exactly modulo p. And because this is 1 mod p, we'll get w mod p, and w will be small. Okay, we dealt with that already. It's smaller than p, and so we'll get w exactly. Now, once we have w exactly, we can, we did operations modulo p, but now we got something exactly, right? So we've lifted out of modulo p. We're free from modulo p, right? And so what we can do is we have w exactly, and then we can reuse the same chain of polynomials to do operations modulo other primes. Okay, so what we'll do is we'll reduce w modulo some small primes. It can just be the first whatever primes. I think maybe they have to. There's certain conditions, but small primes. And since we have w exactly, we can use this chain of polynomials to get v to p minus 1. Since we have w modulo as primes, we can get v to the p minus 1 modulo those primes.
Is there a reason not to just do this modulo 1 big prime?
No. Not that I can think of at the moment.
You probably could. It might be a little faster.
Yeah, I mean, efficiency, it would be faster, I guess. But that's just the way I think of it, I guess. But it's not necessary. So then we're going to repeat this whole process for a different prime, big prime, p prime. I guess it's sort of a bad name. Maybe p star would have been better. But, anyway, so we picked this initial prime p, which is really big. Whereas this prime here is just going to have the same properties. It's just going to be different. And it has to satisfy this condition that the GCD of those two numbers is 2n. Okay? Both of these primes are congruent to 1 mod n. Now, Now that we have v to the p minus 1 modulo some large enough prime or product of primes, and we also have v to the p star minus 1 modulo those same primes, what we can do is we can take the GCD of these things up in the exponent, right? Sort of do an extended Euclidean algorithm in the exponent there to recover v to the 2n modulo the primes. And v to the 2n is nice and small. 2n is small, right? We can write this. We can write v to the 2n down. Okay. Right, we had it modulo some primes, and then we can recover it exactly. And then there's a way to recover v from an exact power of v that you can write down.
Is doing this with the p prime as well actually faster than just getting v to the p minus 1 mod q, taking the p minus first roots, which gives you two different possibilities, I guess, and then just trying them out and figuring out which one is correct?
I didn't quite get all of that, but it could.
Well, I mean, I guess they're all correct.
Instead of just using p prime, you just want to use p.
I mean, yeah, just take v to the p minus 1 modulo q, make sure that the GCD of q minus 1 and p minus 1 is 2n, so there are only 2n different p minus first roots.
That is not
you can
true.
Q.
There are 2n to the power 2n because the prime split completely, so you have loads of n fruits.
I mean, maybe you'd pick a prime that doesn't split completely.
But then you have totally.
I mean,
these primes split completely,
I mean,
and that is
yeah, what I'm
huge.
saying is let q be a prime in the field that we're working in. And then just compute things mod q, take a p minus first root mod q, which you can't quite do because you have these 2n different units mod q.
So you like to have an inward prime. But your x to the n minus 1 reduces, so every prime splits. You're not having a number field here. You have a
Look at the big part that is a number field.
I think in principle it should work, but there are problems to solve.
Maybe from v to the p minus 1, you can get v to the 2n with some algebra tricks and ignore the p prime. And then you still have to do something to get v from v to the 2n.
Well, I mean, you could, fine, you could, I mean, if this works, it would give you v to the 2n mod q. But I'm saying you could just pick a 2n root mod q. And I mean, that'll recover v up to units.
In the complex numbers, maybe. But
Well, I mean, up to multiplication by plus and minus 1 in powers of x. You're not going to do any better than that.
Okay, so
it's a little bit of a challenge.
yeah, so they probably. It sounds like it should work.
If you embed it into the complex numbers with one of the embeddings, you can just take the 2nth root of it. But there's 2n of those,
Yes.
and you look at the other complex embeddings,
Yeah, you have to.
there's more choices there. So how do you do it in a consistent way?
Well, I'm
It
saying
doesn't
do this modulo some prime.
Well, that's the trick, that
Yeah, but I'm
the
saying.
actual way we did this, they use another prime to get the sort of conjugates. I had some formulas for that. I'm not sure. But we all agree that you can get v from v to the 2n at least.
Modulo primes, you have the same ambiguity. You go modulo, you don't have inward primes and you don't have domains. So you have loads of n fruits. There is an issue there.
Okay.
Well,
You
I
wanna
mean,
wait till
but,
So I think you did this in your paper for n prime, and then the CRT is much easier because you just have two problems. You have two fields that are involved. And then the number of possibilities to try out is far fewer.
In the paper, we did a computation in, we evaluate at a root of unity,
Right.
and then you use some algebra to find out
the values of the other roots of unity?
That was for n prime.
Oh, this would be like n prime.
Yeah.
Oh, yeah, right, yes, okay, right.
And a prime number. And then you take the trivial root of unity, of order 1, and then you combine. That's what you did in the paper.
Yeah.
But if n has many, many divisors, you run into combinatorial explosion.
Oh, and itself has divisors.
Yeah.
Right, okay, well, we didn't focus on that case. So I think you did in your,
Yeah.
you had to do that for your work.
Right. And you can do it, but it takes work.
But we didn't do that part. We only did it for n prime.
Maybe we should put it in our list for the rest of the week.
All right, so any questions about that part? So Mike will give you more details. I just want to point out that this, what we did here has some conceptual similarities to, say, Coppersmith's method. What is Coppersmith's method? Well, he has an algorithm for finding small solutions to univariate modular equations. And essentially what he does is he constructs a lattice of polynomials, given some initial information. He constructs sort of higher degree polynomials that all evaluate to 0 modulo n, where say n is a number that's hard to factor. And then he applies LLL to obtain a small polynomial that evaluates at a small number x to 0 modulo n. And then he says, well, h and x are so small that, in fact, if it's 0 modulo n, it's just plain 0. And at that point, you don't have to worry about n anymore, and you just take the root. And it has some similarity to what we're doing here, where essentially we're finding a way to lift out of a particular prime. So once we obtain this, we just use the fact that well, this is small and this is 1 modulo p to get an exact equation. So it just seems like a nice, it's one of the nicer ways to sort of combine algebra and geometry to get stronger algorithms against algebraic problems that involve some sort of smallness. Okay, I promised that I would talk about implicit lattice reduction. This is where what we wanted to do is we had, well, I'll just tell you the claim, and then hopefully you can see how it relates to what we needed for the algorithm. So the claim is that for any v in the ring, if I give you the relative norm in the real subfield, and some h and f basis, say, of the ideal associated to v, then we can efficiently output some element in the ideal such that the multiplicand is small. Okay. Normally, LLO would guarantee some bound on the length of v times a, not just a. And so observation is pretty simple, actually. LLL, when it's actually operating, or I guess any lattice reduction algorithm, when it's deciding to swap or do a size reduction, it just looks at the mutual dot products of the vectors, right? It looks at things like size and, And so all of this can be computed just from the grand matrix associated to the basis. Okay. And the same is true for ideal lattices. So if we, in general, what happens for ideal lattices is that we have some bunch of vectors that are in the ideal I, a bunch of polynomials that are in the ideal I. And what we have from v times v bar is essentially all the sort of the mutual products with the conjugates of all of these different polynomials, elements. So in particular, I mean, what we actually have are just the UIs times the conjugates of uj for all I and j. But from that, just by dividing out by v times v bar, we can just get all these quantities for the a's. Yep.
So basically what you're doing is you're finding a short vector in the ideal v divided by v bar or something.
Yeah. Yeah. And then we just apply LLL directly to the a's. And what happens when we do that is that we get some unimodular matrix that represents the transformation from, you know, our initial basis to some other one. And well, if you just follow it through for each step, I mean, the guarantee on LLL is the same. The a's are smaller than 2 to the n over 2. And you know, so it's maybe a little hand wavy, I guess, but really it is just a matter of dividing out the geometry of V, and you get something. You just get the multiplicands exactly, their geometry, and you just operate lattice reduction on that, and that just propagates through the entire algorithm. You end up with something which is where the A is small.
So what you do? You apply the operator. So you know the gram matrix of V.
Mm-hmm.
You also know the gram matrix of U,
Mm-hmm.
which is your current basis, the basis you are trying to reduce.
Mm-hmm.
And so using these two, you can get a gram matrix of A.
Yeah.
Yeah. And you reduce A, working on the gram matrix, but then you track the operations on U at the same
Yeah.
time. So using the coordinate system of U.
Mm-hmm.
Okay.
That's a good way to say it.
Does that make sense?
Another way you wrote up in a recent paper of using the different embedding, right? You divided by, you know, the
Oh,
complex embedding.
yeah, I mean, maybe I should have done that for the presentation also, but just working directly in the cyclotomic field is, I mean, there's a way to express all of this nicely in terms of the embeddings.
Did that help generalize it to number fields? To arbitrary number fields when you did it that way?
Well, it's just cyclotomic number fields that so far we know how to do this.
I'm sorry, right.
Yeah, I mean, it would be interesting to try to figure out what's so special. Well, I mean, that's the symmetry part, I guess. Why is it just cyclotomic? So let's see how I'm doing on time. Well, I guess I
I
can.
have a comment.
Oh, yeah?
I think that there were parts that we implemented and parts we did not implement.
Yeah. So the first two steps we
Which
actually
ones-
implemented.
Which things we implemented, which ones we didn't?
Yeah. Yeah. The first.
Some people want to try to do this at home.
Which first two steps are you referring to?
The lifting procedure where we got rid of the reduction modulo Q, which I didn't talk about at all. It was just a preliminary first step.
Okay.
And then the second step was the averaging attack where we obtained V times
So
V
these
bar.
polynomial chains have never been implemented?
Right.
Oh, okay.
We did calculate the asymptotics, and it was pretty formidable.
Oh, okay.
Because I mean, you're doing a chain of lattice reductions, right? Lattice reduction already is, you know, even if you're doing the polynomial time version of them, is not exactly fast. And then on top of that, we have a chain of them.
Yeah.
Yeah. So we didn't implement that.
Great student.
Considering that lattice reduction gives, you know, much better basis of the exponent than 2.
Right. So in practice, yeah, that could, I mean, that would make a huge difference if it's like 1 to 0.05 to the nth power or something. It would still probably be pretty slow, but Okay. So these are some kind of rough things that I put together at the last moment, so let me apologize in advance. But so as I said, Mike is going to talk about the polynomial chains, so I thought I'd make his presentation relevant by wondering if we can get rid of polynomial chains. So really what we needed for this scheme is, what we had in the scheme is we had this big prime p, and we said v to the p minus 1 equals 1 mod p. Okay, so, but it would be fine if we just had some, small r, The size of this exponent is really what made everything really inefficient and why we needed the polynomial chains, right? So, but what if it were the case that for some small r, we could say that v to the r equals 1 modulo q for a big q, okay? Not necessarily a prime q, but some big composite number, say. So q is still bigger than the LLL bounds, And as long as that's true, then maybe we can say everything works, and maybe we can actually write v to the r down, and we don't have to worry about polynomial chains, which are really there just to get around the fact that we had this v to the p minus 1, which was just gigantic. So can we achieve this? Can we have small r and big q? You're probably going to catch me in all sorts of nasty errors, but so I guess that's part of the fun, right? So okay. So let's set R to be this form. For certain technical reasons, we still wanted to have a divisor of n, but otherwise, let's say that R is just a product of a lot of small primes, the first k primes. And let's just imagine k is log n, basically. And what do I want q to be? Well, I want q to be the set of all primes such that p minus 1 divides r, right? For all primes p where p minus 1 divides r, then v to the r equals 1 modulo that prime. Okay, so we just want to have a lot of primes big P such that p minus 1 divides r. And that's kind of why we chose r to be smooth, right? Because there are a lot of different possibilities, right? Okay. So this is, I went all LaTeX on you. Sorry about that. But so let's try to estimate how big r is. Well, r is just the product of the first, k prime, so that's hopefully pretty standard stuff. What did I do here? I did something.
Log of r equal to the log of r.
Yeah, that's a little weird. Log of n, yeah, sorry. This should be a log of n, sorry. And then, yeah, so the sum of the logs here, you work it out. Prime number theorem, and you get you get this. Okay, and if n is already yeah, so log k is already like log n, then basically the k log k is the big part of that answer. So we can say that r is sort of like this quantity here. It's like 2 to the k log k. So that's kind of small, right? I mean, k is like log n, so it's like 2 to the log n times log n. That's kind of small. Unfortunately, it's not polynomial, and that will make this attempt at an algorithm be not polynomial, because it's going to run in time proportional to r. But still, it's kind of, I don't know, maybe there's something there. So, anyway, so r is kind of small. Now let's look at how big, let's check that q is big, right? And q has to be as big as the LLL bound. Can we achieve that? So I'm making all sorts of, I don't know, heuristic estimates here, but okay. So, so how big is q? So I want to set t to be the set of numbers of this form. those are the ones where, you know, well, so t minus 1 actually equals something that divides R, right? And this is some subset of the primes, right? So in that case, t minus 1 would divide, or you know, whatever element in there minus 1 would, right. Now let t prime just be the subset of those numbers that are prime. So now I just want to guess that, well, by the prime number theorem, you can just say, well, you know, number of size t has a, you know, 1 over log t chance of being prime. So if we make that heuristic estimate, then what you get for the size of q, which is the product of these primes in the set, is oh wait, I'll let you stare at it. I don't want to say it, but is that basically if you follow it through, that the size of q is as big as 2 to the n. So it's possible to have a quite small r, a quasi-polynomial r, and still have a q that's large enough to apply the LLL. So, okay, so the answer for can we avoid polynomial chains is, well, not quite in the sense that this is a quasi-polynomial time algorithm, because r is quasi-polynomial. To write down v to the r takes quasi-polynomial time. So that's too bad. This approach can actually, it has an interesting extension. You can actually, sort of our original algorithm sort of requires precise, the precise quantity v times v bar. Right, whereas this approach can actually be extended because it doesn't go through all the messiness, I guess, of the polynomial chains, and it doesn't, you know, well, and also it's not exponentiated by such a huge number. As long as you have a 1 plus 1 over r approximation of v times v bar, everything basically still goes through.
So before you, this is an extension thing, but before your extension, you're saying you have an alternate algorithm for our problem that's probably faster, but this is not polynomial.
Yeah, I wouldn't want to, I mean,
It may not be.
I wouldn't want to estimate, or,
The speed of it.
yeah, I mean, depends on the parameters. I just have no idea whether it's faster or not. I just think it's, yeah, I mean, it leads to, I mean, maybe something better can be found here that would make this polynomial time, so it's just an idea that doesn't really work. And secondly, it has this property where you can take, you know, instead you can take very, you know, approximate. So one of the things in the attack on NSS, on the intrusive signature scheme, was that we really needed the coefficients of v to be really small so that we take the averaging attack. We only needed a polynomial number of samples, and then we could round. Right? That only worked if v times v, if v was very small. But so, okay, fine. Set v to be bigger so that that attack doesn't work. Right? And just increase all the parameters just a little bit. Well, this says that, well, no matter how big you set the coefficients of v to be, as long as you can obtain an approximation that is close to a sufficient factor, then you can take this and use this algorithm to actually recover v. So
here, the choice of R is much smaller than the choice of P there. Could you use polynomial, those chains here, and work with the smaller R and mix both of them? Do you think that will get any improvements? Like you then still don't have to write the v to the R, but you're using these polynomial chains for a smaller R than.
yeah, yeah, I don't really know. So yeah, one, that might speed things up a little bit because it's more direct, and two, there might be some way to work with the polynomial chains, but still, yeah, I mean, I don't see why it wouldn't work. That you could work with the polynomial chains, and things would still work for an, you know, if you're off by epsilon for the approximation of v times v bar. Yeah, so I don't have a great answer, but yeah, I mean, it's a good idea. Okay, so this is the final thing. I want to talk a little bit about just how strong are principal ideal lattices. Okay, so unfortunately the GS algorithm shows that principal ideal lattices seem not to be as hard as general lattices. Doesn't mean we can break them necessarily, but what it does imply is that if you have any n-dimensional principal ideal lattice in the cyclotomic number field, then you can use the GS algorithm to show that obtaining a 2 approximation of SVP in this principal ideal lattice is basically only as hard as solving SVP in an n over 2 dimensional lattice. It means that I have to output a vector that is no more than 2 times as long as the shortest. Intuitively, you think, I think this probably has something to do, you know, principal ideals are generated by 1 generator. Most ideals are generated by 2 generators. So maybe that's essentially the obstacle here. That you know, what's going on here, that principal ideal lattices are in some sense half as hard. Well, not half, actually much less than half, but their dimension is only half in some sense.
So
Yep.
if you keep going this way, you can approximate SVP within a factor log n in polynomial time. Is it true or not? If you keep halving the dimension.
Oh, this isn't necessarily a principal ideal lattice, right? Okay. I'm just saying.
You cannot repeat it.
You cannot. No, this is just this is something else.
No, within a factor n, you would get a factor n. Okay, but that's a general lattice. What you get.
It's not exactly general, but it's not the same thing.
You
Yeah.
cannot repeat.
Yeah. Yeah, I did say some lattice. Yeah, that would be. I can see why you would be scared. Yeah, so breaking. It does seem like breaking principal ideal lattices is a bit easier than breaking general ideal lattices.
So will V be known here?
No. It's just the.
That exists.
Huh?
A promise that there exists, a promise that it is principal.
Yeah, just a promise that it's.
Okay.
It's principal.
Wait, principal ideal lattices being from any number field from
No, cyclotomic. Yeah. All of this relies very heavily on cyclotomic. And really it comes down to somehow to the structure of the units and the fact that they're all in the sort of index to subfield.
The principal ideal lattices always have by far the shortest vector for every number.
What do you mean?
That if you write down an ideal lattice, did I say principal?
Yeah.
Yeah. If you write down an ideal lattice, then if you look at the ones that you get from principal ideals associated to the number field, they are always the most skewed. They have the shortest vectors. That makes it easier.
So typical generators are short.
Yeah.
But I mean, they certainly could have large generators
Yeah,
of it.
you can hit them with units. But
Okay. So how does this work? Well, you can kind of tell by the slide that I was a bit of a rush here at this point, but so this is my final slide. There's not even a goodbye or anything after this. So how does it work? So this is how it works. So we're just given the ideal I, and okay. And what we're going to do is we have what we can do with that ideal is that we can generate a basis of this for the principal ideal generated by this special element, which is V over V bar. Okay, that's not so difficult to take the basis for V to get the basis for U. Now, the funny thing about U is that if you look at U's relative norm, well, then it's just 1. right? Because you take its conjugate and it just flips it over. Its conjugate is v bar over v, right? I'm just saying we don't actually have u in our hands or anything. I'm not saying that. What I'm saying is that u has a special form, and it happens to be the case that u times u bar is just 1. So what does that mean in terms of, v times v bar is basically the geometry of u. It means that its gram matrix is just a multiple of is the identity. Right? It means that u is just an orthonormal. Its rotation basis is just purely orthonormal. Okay? So, I mean, we don't have u in our hands yet. We just have a basis for this ideal, which happens to have an element in it whose rotation basis is orthonormal. Okay. So what that means that we already have it is that we don't have to be given it, right, for the GS algorithm, right? So we already have the ideal for u, and we have u times u bar. It's just 1. Okay, so we can apply the GS algorithm, and we can recover u. So that's kind of interesting already. I mean, we started off with a general principal ideal, associated to some v. We've obtained some really, shocking information about v, namely the ratio of v and v bar. Yeah.
Hi, that's a quick question. The original GS algorithm requires that v is small. In other words, has small entries. I don't see how the algorithm would be applicable in the case of u.
I don't. Why do you say it requires small entries? I mean, there's certain things like the averaging attack, right? I'm not talking about that part of the attack. I'm just talking about the third step where we.
Is it only the, okay, I'm sorry. Okay, yeah, you're right.
Right. Okay, so we actually have u in our hands now. Okay, so, yeah. So what can we do? Let me see.
It should be 1 plus 1 over u, I guess. U bar is 1.
Yeah, I did something weird here. Okay. I'm too sleepy to figure this out. Let's see. Yeah, so I mean, if we just took 1 plus this quantity, that would be v times v bar, v plus v bar over v. No, sorry, over v bar. And then we can take the bar of it, okay? And we can get the v plus v bar over v, which is what I want here. Okay.
So we get 1 plus u bar.
Right. And then since we have the ideal for v, we can multiply it to get a basis of just the numerator here. So now we have the basis of something which is in the is real. It's in the index 2 subfield. Okay.
Why didn't you just from the start compute the ideal for v times v bar, which is in the index 2 subfield?
No, that's v times v bar. We need v plus v bar.
Well, with v times v bar, you can run the whole procedure to just get v when it's ideal. Or with v times v bar and v divided by v bar, you can multiply them and get v squared.
Say that again.
But you don't know v times v bar.
I mean, you know the ideal v times v bar.
Yeah.
Just the product of I times I bar.
Uh-huh.
And it should be generated in the index 2 subfield.
And you want to find that somehow?
Yeah.
Yeah, I don't quite get it.
I'm not clear why we're working with v plus v bar instead of v times v bar.
I don't know, maybe it does. No, the shortness doesn't matter.
V plus v bar is slightly smaller.
Yeah, I just don't know if all these transformations end up working, but maybe there is some way to make it work, I'm not sure. I mean, it does seem like there are a lot of unnecessary, I mean, like it seems more complicated than it should be. But so maybe there is something more direct, I don't know. Okay, so, so we have a basis of this. And then I just want to, we have a basis of this in the sense that it's this element times a bunch of elements in R. And we can project that down to get this element, which is already in the index 2 subfield. That element times a bunch of elements that are in the index 2 subfield. We can just project it down, you know. We have the original n-dimensional lattice, and we can just screen out those things that are not in.
You intersected with K plus?
Yes.
Okay.
Right. So at this point, we have things of this form times r's that are all in the index 2 subfield. Okay. And then, right, let's see. Right, and we have this, this ratio from, well, this is just sort of the same thing that we did before. We have that ratio exactly. We can multiply that through, and then we get v times a bunch of things that are in the index 2 subfield. And, yeah, so, so that just means that we're searching over over two-dimensional space at this point, right? Right, we have v times a bunch of things in, you know, n over two-dimensional space. And I'm not sure why I said this was a 2 approximation. I thought I had some reason. But anyway, this is the least worked out slide, so it's a strong finish.
You wrote about this in one of your papers?
Yes,
So there's details somewhere published.
Yes.
In which paper? This was
The multilinear maps paper, yeah.
and you said at the beginning that you might say something about applications. Is there more that you?
Well, this is what I meant by application, right? So a stronger attack on principal ideal lattices. I mean, so it's not just a matter of.
So is this one of your half lattices, and what is the other half? You had 2 lattices of half the dimension that you were announcing, or not? On the previous slide, or do I miss something?
Go to the previous slide.
Or, oh, this is one, okay.
Yeah, so the n over two-dimensional lattice is just v
okay.
times
Okay.
stuff in that subfield.
Okay, okay.
Mhm.